In this segment, I'd like to talk a little bit about where the atoms that make up all the stuff that's around us, where those came from. So, we're calling this lecture The Origin of the Elements. And I'm going to start off with a question. And that question is, how old are you? Well, that's a fairly straightforward question, one you can probably readily answer. Myself, I am 43 years old. Okay, easy enough. How old are the atoms that make up your body, right? We know that you and I are made up of atoms, right? A whole bunch of atoms. We're going to talk about what kinds of atoms here in a minute, but oxygen, hydrogen, stuff like that, nitrogen, right? That's what we're made of. So, if you're, 21 years old, what's that mean? How old is your body? Well, I guess 21 years old, sort of. How old are the atoms that make up your body? We're going to get to that too. Where did those atoms come from? Did they come from your mom? We're constantly replacing the atoms that are in our body, actually, right? Our skin is constantly new, right? Our body is constantly rebuilding cells and repairing cells. So we're constantly replacing the atoms that are in our body. So I don't think they came from your mom. Where'd they come from? You can say the food that you ate. Okay, sure. How'd they get in the food you ate? Those are some questions we're going to talk about in this lecture. So this is a picture of Carl Sagan. He's one of my heroes. A great astronomer, but mostly a great science teacher. Carl Sagan is the reason why I am a physics teacher. He had a program on PBS when I was a kid called Cosmos, and I loved it. And it was an accompanying book, and I wore it out, man. And so Carl Sagan's a great educator, a great science educator, and a great man. And he says, if you want to make an apple pie, what do you need? Well, this is a question for you, not Carl Sagan. What do you need to make an apple pie? From scratch. Let's add that. What do you need to make an apple pie from scratch? Well, you need some apples, you need some sugar, you need some flour, a little butter for the crust, a little cinnamon, a little water maybe. I don't know. That's not really from scratch though, right? So you gotta go to the store and you gotta buy flour. If you really want to make apple pie from scratch, you must first invent the universe. This is what Carl Sagan says. Why? What does that mean? What does that mean? Well, because what's an apple pie made out of? Well, he just said flour, butter, sugar, apples, right? But what are those things made out of? The elements. Same stuff you and I are made out of, right? So, in order to make an apple pie from scratch, we got to first make some hydrogen, some oxygen, some nitrogen, right? Because that's what goes in to the parts that make up an apple pie. Kind of interesting. So here's what we're talking about. Here are all the elements, right? So far we've learned that there are 92 naturally occurring elements. And that all of the stuff all around us is made up of those 92 naturally occurring elements. Different combinations of those 92 elements. Whether you're talking about an apple pie, or a hedgehog, or a human, or a USB stick, guess what? Every single one of those is made out of combinations of those 92 elements. Where'd those come from, though? Are they being made new ones all the time? Or have they been around for a while? Well, let's think about you. So we already asked the question, how old are you, right? And I answered that question with, I am 43 years old. What am I made out of? Well, I'm made out of a whole bunch of atoms, right? The atoms that make me up form molecules. Those molecules form cells. Those cells make me. Okay, great. So 96% of the human body is just 4 elements. Oxygen, carbon, hydrogen, and nitrogen. That's it. 96% of us are oxygen, carbon, hydrogen, nitrogen. Guess what else is oxygen, carbon, hydrogen, nitrogen? Oh, an apple pie, a hedgehog, right? All kinds of stuff is made out of those 4 elements. If we include the 6 most abundant elements, then we add phosphorus and sulfur in there. But that's it. Those are the six most abundant elements of life. And there's a few other little scattered things in there. You need a little iron. You need a few of other things to make a human, right? But 96% of our body is made up of just four elements. So oxygen, carbon, hydrogen, nitrogen. Where did those come from? Where did the oxygen, carbon, hydrogen, nitrogen that you were made out of, where did those come from? How about the Earth that we're standing on? We could ask the same question about the Earth. How old is the Earth? Yeah, something like 4.5 billion years old. That's pretty old. You know, the universe, as far as we can tell, is something like 14 billion years old. So, yeah, the Earth's been around for some fraction, something like a third of that time. How are the atoms that make up the Earth, though? Are they that old? Older? Newer? Well, it turns out you need a slightly different ingredients to make up the Earth than you do to make up a human. 98% of the Earth's mass is just in 8 elements. Iron, oxygen, silicon, of course, those showed up in our 8 most abundant for life. But then we've got a bunch that didn't. Magnesium, nickel, calcium, aluminum, sodium. These are a bunch of metals, aren't they? A bunch of pretty heavy metals. Where are those located? Well, mostly in the core of the Earth. So this is most of the mass of the Earth. 98% of the Earth's mass is just those 8 elements. Now on the crust, it's a little bit different. We get more of the ingredients for life on the crust, but you know, it's still not that different. Where did all these things come from? How old are all of these atoms? Well, let's start with hydrogen. Hydrogen is the oldest of all of the elements. So the universe started off in the Big Bang about 14 billion years ago. And it's been expanding ever since. Expanding into what? Yeah, I don't know. You know, let you lose some sleep over that idea. So universe is expanding. It's been going for about 14 billion years. The first electrons formed just tens of milliseconds later. So in the beginning, it's this infinitely small, infinitely hot, right? Super high energy, super tiny, everything's all smashed together. As it expands, it starts to cool. And so in the beginning, there's nothing we would really associate with mass, right? There's no stuff, nothing you could hold in your hand. But as the universe expands and it cools, we start to see particles formed. The first particles that are formed are the lightest particles, the electrons. They're formed tens of milliseconds after the Big Bang. So fast forward just a little bit, and we start to get hydrogen and a tiny bit of helium. So after the electrons form, the protons form. And then the universe has to cool down a little bit more before the protons and the electrons start hanging out together, and they form hydrogen. At that point, now we've got some matter. We've got some stuff that you and I would recognize as matter. As it cools a little bit more, we start to see a little bit of helium formed. This takes about 370,000 years, approximately, for this to happen. Now, as the universe expands and it cools, some places are just randomly a tiny bit more dense than other places. And so guess what? They're more dense, they have a little more gravity, and they attract more stuff. So random variations in density lead to increased differentiation. The denser areas get more and more dense as they accumulate more and more stuff, and that makes the less dense areas less and less dense. Some of those places that were really dense, they start accumulating enough stuff that they actually form stars, right? In the center of a star, in the core of a star, what's happening? Well, it's a process called nuclear fusion is happening in the core of a star. That's what's powering our sun and all of the other stars that you can see when you look out at night. In the core of a star, there is so much pressure, and the temperature is so high, and the atoms are packed together so tightly that they start to really sort of bump up and overlap with each other, and sometimes you can get a situation where 4 hydrogen atoms smash together and they make 1 helium atom. This is called nuclear fusion, and it's different from a chemical reaction, right? In a chemical process, we have all the same atoms before as we have after. We start with the same atoms as what we end up with. In a nuclear process, we actually make new kinds of elements. And in the sun, that's happening through a process called fusion, where lighter elements get smashed together to form heavier elements. And when that happens, a tiny bit of energy is released. That's what's powering our sun. Okay, so that energy gets released, and then it's got to get out somehow, right? And so it's released in the form of light. And so that light energy has to get out from the core of the sun, right? It takes something like 50,000 to 500,000 years, somewhere in that range, for light that's created at the center of our sun to make it out to the outer edge, right? So this light streaming out from the inside, it creates a pressure heading outward in the star. It helps to keep the size of the star. It actually pushes outward on the matter of the star, making it a little bit bigger than it would be otherwise. Pulling in, we have gravity. So the shape of a star, it's this balance between the inward pull of gravity trying to smash everything together and the outward push, what we call radiation pressure. And it's really that light. It's really this outward push of that light and that energy trying to get out from the center of the star. And so this process is happening at the center of the star. In our star, it's mostly combining hydrogen to form helium. But you know what? As pressures increase, helium can combine to make things like carbon, slightly heavier atoms, right? You might get a little helium, a little hydrogen, get together, make some nitrogen, right? Neon gets made. All of the different elements get made. And when that happens, a tiny bit of energy gets released. Tiny bit of energy gets released. And so this happens all the way up to iron. If we were to peek back at this periodic table, iron we see is right here. It's number 26. Right? And so all the way up to iron is formed in the cores of stars just naturally burning. So helium might combine to create boron, might combine to create nitrogen, might combine with some phosphorus to create some iron. Or we might get some manganese or some chromium. But something changes when we look at elements heavier than iron. When we look at elements heavier than iron, then something is different. And what's different is that when you smash two atoms together that are heavier than iron, you don't get energy out, you have to put energy in. And so iron is this like transition point. And it's the heaviest element that gets made under the normal process of a star functioning. So all of these elements, we started with hydrogen that got formed just right after the Big Bang, and a tiny smattering of helium. That's it. Afterwards, everything else in the periodic table had to get made in a star. And that got made under normal circumstances. And by that I mean, as normal as a star is, right? I just mean like inside the core of a star, nuclear fusion, like our sun, right? That's happening in our sun right now. The elements up to iron are being formed. But in order to form these heavier elements, say gold or mercury or thallium, right? In order to form those, you have to input some extra energy. And it doesn't just happen on its own in the core of a star. So looking at this, we've got carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. These are all of the most common elements in life. Notice where they are. Carbon, nitrogen, oxygen, phosphorus, sulfur, hydrogen. They're all lighter than iron. So you and I are almost all made of this stuff that formed in the core of stars. Now the Earth, however, notice it's got iron and some heavier stuff too. Right? So where did that stuff come from? So elements up to iron were formed in the fusion of cores of stars. So we just talked about that. Elements heavier than iron were formed in supernova explosions. So towards the end of a star's life, right? I've said we've got this balance of the outward radiation pressure and the inward pull of gravity. And the star is just using up this fuel just faster and faster and faster as it gets hotter and hotter and hotter, right? And as the pressure in the inside there, it gets higher and higher and higher. And then it burns up. And it ends up using up all its fuel in a short amount of time, right? These stars live for billions of years. And then over a course of minutes and hours, that fusion shuts down because it's run out of fuel. The temperatures start to drop quickly. And this outward radiation pressure goes away. And what happens? That star starts to collapse. Gravity starts to take over. And it collapses, and it happens so fast, on the order of seconds, This star that's been alive for billions of years, it dies in this spectacular fashion where all of a sudden the star collapses and it sort of recoils off of itself and it spews its stuff all over the universe. This is called a supernova, and it's one of the most spectacular events that happens in our universe. When this happens, during that collapse, there's a tremendous amount of energy available. And that is when we get the elements heavier than iron formed. During that collapse, the end of its life of a supernova. This right here is an actual picture taken by the Hubble Space Telescope of a supernova. This supernova happened in 1844. Again, it's crazy. These stars live for billions of years. But the supernova happens like that. And so this is a picture of it still happening, right? So I guess it doesn't happen like that. The actual explosion happens really quickly. But then this is just a picture of that energy getting spewed all over space. So what is in these balls? It's a bunch of stuff. It's a bunch of atoms. It's the makings of another solar system. So when we look at you and I and the stuff all around us, we're all made of elements that are heavier than hydrogen. We've got some hydrogen in there too. But we're made of elements that are heavier than hydrogen. So you and I, we are truly, truly made of star stuff. We really are, right? The stuff that we're made of was once in the core of a star, which is so cool to me, right? And so when we look at the Earth and its composition, and you and I and our composition, I said the Earth is about 4.5 billion years old. And so we've got a lot of evidence that our solar system is a second or a third generation solar system. In other words, the very first solar systems could not have created life as we know it because they only contained hydrogen. As the suns burned, as the suns, went through fusion, I should say. A lot of people say burned, but that sounds like a chemical reaction, right? So as the star uses up its fuel, it's creating these heavier elements in its core, but there wouldn't be any of that outside of the star, the way there is in our solar system, if we're talking about a first generation solar system. Once that first generation solar system ends, right, in a spectacular supernova, now we've got the ingredients of life spread out throughout the universe. So our solar system must be at least a second or possibly a third generation solar system, which is kind of crazy. Now, a star has to be quite big in order to undergo a supernova at the end of its life. Our sun is not big enough to do that, right? So our sun will as it heats up, starts burning that fuel inside, it'll eventually become a red giant, and it will swell as the radiation pressure sort of for a time sort of beats out the gravity pressure. Then that the red giant will form, and it'll certainly encompass the orbit of Mercury, Venus, possibly even the Earth, right? So it will become much, much bigger than it is now. And then as it uses up its fuel, instead of collapsing in this sudden demise, it will instead slowly collapse down and cool down and eventually become a brown dwarf, which is a cooler star that has run out of its fuel. So it's only the biggest stars that die in these spectacular supernovae. But thank goodness that they do, because that's what made the stuff that you and I are made out of. So, here's another Carl Sagan quote. "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." Right? And so here we are thinking about the stuff that we are made out of. A nebula, this is another Hubble picture of the Orion Nebula. And a nebula is a place where stars are formed. So this is a big cloud of gas, and in the densest parts, they're collecting more and more stuff. They're accreting more and more matter, and eventually stars will be born in these nebulae. Okay. Here's a couple questions. So, which are older, the atoms in the body of an elderly person or those in the body of a baby? Well, what do you think? Hopefully, you think they are the same age, which is appreciably older than the solar system, right? So whether we're talking about a baby or a grandpa, the atoms that make up that person are exactly the same.